So I would like to tell you a little story about the error of time in a quantum system. So the talk is going to be divided into two main parts. In the first part, I will first introduce the thermodynamic error of time and then show you how to characterize irreversibility. I will then present the results of an experimental observation of the thermodynamic error of time in a driven spin 1/2 system. And in the second part, I will try to convince you that the error of time can actually be reversed in a system with initial quantum correlations. And I will finally present an experimental observation of such a reversal in a bipartite quantum system, 2 spins. So let's start with something that I guess you all know, namely that macroscopic processes do have a preferred direction of time. Half of the audience is having a cup of hot coffee or tea in their hands. If you put it on the table, leave for 20 minutes, come back, the coffee is not going to be warm anymore. It has thermalized with the room or at room temperature, and you might repeat the experiment, come back after another 20 minutes, and unfortunately the coffee will still be at room temperature, right? So heat flows from hot to cold. That's one way to summarize it. And so the reverse process does not occur spontaneously. And this is what we call irreversibility in general in physics. You also all know that in thermodynamics, irreversibility is characterized by a mean entropy production, which is always positive. Using equations, a process is called irreversible if the mean entropy production is strictly positive. It's called reversible in the limiting case where the entropy production is 0 on average. And this is not, called it impossible, but no one has ever observed a process with a negative mean entropy production so far. And in 1927, Eddington called this time asymmetry the error of time. And the name was so sexy that we're still using it today, 90 years afterwards. I should also emphasize I'm talking about the direction in time and not about the direction of time. Well, there is no way to reverse the direction of time.
Did Eddington mean the thermodynamic error or the cosmological?
No, the thermodynamic error of time. I double-checked the book. Yeah. He talks about many different errors, but the section where he talks about the thermodynamic error of time. There's a very nice discussion of the error of time using the example of a reversed movie, which you can find in Chris's review published in 2011. And I'm going to build up on that intuition, reversing a movie and then see what happens. So that's the movie. Hoping that it works. Black. It works. So what you see here, I hope you see it from the back, is it sharp enough? So it's a video that you can find on YouTube. What you see is a small boy on a swing that's actually the son of George Porter, famous chemist who got the Nobel Prize for his study on very fast chemical reactions. And the question is this movie played forward or backward? Can you tell? Until the end. No. Can you tell during the duration of the experiment, right? I'm going to show that movie. Well, it's a lecture on thermodynamics that he gave in 1965. You can find it on YouTube. Backward or forward?
Back.
There's another example coming from physics, a set, an ensemble of pendula, forward or backward? Can you tell? Can the experimentalist say something? I would say the entropy production in all these examples is so small that you cannot, over the duration of experiment, tell if it's backward or forward. Another example, you see George Porter's hand. He's moving bricks from one place to the other. Is this movie played forward or in reverse? There's no way to tell. I think that's the fair statement. That another example, mixing balls, dark and white balls. Is this played forward or backward? There's no way. So in all these examples, the entropy production is close to 0 on average. So these processes are quasi-reversible. Let's check.
Is there a good definition of what's quasi-reversible?
Entropy production almost 0 during the
almost 0, but
yeah.
I mean...
Well, I just need to comment. I don't need to comment too much, right? The same question, played forward or backward, I think it's pretty obvious.
So quasi-reversible is that the differences cannot be observed.
Yeah, that's my definition of it. He's unmixing dark and white boards, it's clearly played backward. Right? Another example, you have a particle at the minimum of a potential well, and it's slowly gathering energy out of the thermal fluctuations around, gaining momentum, gaining velocity, gaining energy. And this is clearly played backward. Right? There's no doubt about that. So all these processes have a positive mean entropy production. Another nice example, again, mechanical system at the minimum of the potential, a ball on the table, and it's slowly collecting energy out of the air molecules around.
This could be also the other way around.
Second last example, and the last example actually. So clearly, all this, you can tell, right? You know if a process is reversible or not just by looking at it. The question is, how do you quantify that experimentally or theoretically? Before I come to that, let me talk about the apparent paradox of irreversibility. People have been talking about irreversibility for more than a century, and the reason is there's an apparent paradox. Naively, you would say, oh, all macroscopic systems are made of lots of microscopic particles, atoms, right? But if you look at the equations of motions or the laws of physics for microscopic systems, they are all reversible. So for instance, start with Newton's laws of motion. I don't have to describe it. What is important to notice is that there's a dt squared here. So meaning if you try to play the process backward, you replace t by t prime, which is the total duration of a process minus t, you immediately get that dt prime is equal to minus dt. That's time reversal. However, if you take the square, you don't notice any difference. So Newton's equation of motion is invariant at the time reversal invariance. This is also true for Maxwell's equations, for Schrödinger, Dirac, and you can continue the list. Now the question is, if all the equations of motion for microscopic particles are time reversal invariant, how come that macroscopic processes do all occur in a preferred direction? What's your take on that?
Coarse graining?
Much easier. Initial conditions. The answer is to recognize that processes in nature are not only described by the laws of physics, what we teach students. What we do typically do not emphasize strongly enough, at least I don't do it, or I do it now, is that you also need initial or more generally boundary conditions. So these are fixed, these can be chosen. That you need both equations of motions and initial condition is not new. You can find it in Newton already, 1687. There's a very nice section on that at the very beginning of Wigner's lecture, Nobel lectures, 1963, where he describes this fact. And let me give you a few examples just to stress that point. We all know that planets in our solar system orbit along ellipses. This is a law, Kepler's law. You derive it from Newton's equation of motion. However, they're all quasi-circular in our solar system. This is has nothing to do with Newton's law. It comes from the initial condition. Another example is, if you look at our solar system, they all orbit in the same direction. There is no reason why they should be so. Newton does not enforce that. It comes from the initial conditions. And this apparent paradox should not be a paradox, because the answer was given by Boltzmann himself, 1877. That's quite a long time ago. And I'm going to read that quote just to show you that he recognized the solution to that problem a long time ago. So he writes explicitly, from the fact that the differential equations of mechanics are left unchanged by reversing the sign of time, Herr Ostwald concludes that the mechanical view of the world cannot explain why natural processes run preferentially in a definite direction. But such a view appears to me to overlook that mechanical events are determined not only by differential equations, but also by initial conditions. So Boltzmann, 1877, recognized that you need boundary initial conditions. An example, you take a bottle of perfume and consider different initial conditions. The first one, all the molecules are inside the bottle, and then you open the bottle, and then you can take a movie of that process and play it forward and backward. You immediately notice that this is irreversible. You do the same experiment, but you start with the open bottle of perfume. Clearly, the equations of motions are completely unchanged, but if you play that movie in reverse, you don't notice any difference. So the equations of motion are the same, the initial conditions are different. And then there's another argument which is very often put forward, is that the probability that all these particles gather again inside the bottle is extremely small, because you have 10 to the 24 particles. So typically people believe or think that to have irreversibility you need a very large number of particles, 10 to the 24, which is not true. Namely, if you write, let's consider a simple situation, you write down the second law of thermodynamics for a driven system, and to make things simple, I'm going to consider a process which is isothermal, constant temperature.
I don't want to interrupt your thoughts, I'm not sure where you're going with.
I'm going to get 10 minutes extra. I'm pretty sure. There's no reason why I should get treated differently than an alpha one. Please.
Well, I agree with you. A lot of people would say, well, now then you need to explain why we come from a low entropy initial condition. That would be the...
But that's a very good point. And okay, let's address it now. Because if you accept that the initial conditions can be chosen, the question is where do they come from? They come from as a result of a process that happened just before what you're observing. And then you go back, and at the very end you end up with the beginning of our universe, and you try to connect the thermodynamic era of time with the cosmological era of time. But I'm not going to go, I don't want to go there during that talk. But then very nice papers going back to Hawking we heard about talking about Hawking on Monday. People claim that the thermodynamic era of time is a direct consequence of the cosmological era of time. And then you have probably as many papers claiming it's not true, it's just there's nothing to do with it. Or the opposite, that the cosmological era of time follows from that. I'm not going to go there, right? I'm going to talk about something that can be checked in the lab and have nowhere to verify the cosmological era of time in a lab. At least I don't know how to do that. But let's come back to irreversibility for a single particle system. So I'm going to, you all know that, we heard that several times, that if you consider isothermal processes, meaning a system is in contact with a heat bath during the entire process, temperature is constant, then you know that the average work is always larger than the free energy difference. And this inequality here gives you a preferred direction already. It's enough. Even though you study one single particle, which would be a colloidal particle, a single spin, a single atom, whatever, it's enough. Fluctuations are going to be big, because it's a single particle system, but this inequality appears already for a single particle system. So that's a nice conclusion of a paper written by Campisi and Hengi a few years ago. So to repeat what I, yeah?
Really a single particle because we need a thermal mass.
You should have a single particle in contact with something, and it's the thermal initial state which is going to break the initial time reversal invariance. Sure. So the initial condition is set by the environment, but I can only look at one single system and still see signatures of irreversibility.
Will you get to the same if you have only two particles and not environment? It will be totally reversible.
It's different. It's a different situation. So what I'm considering is that you have a heat bath which sets the initial thermal state, and this thermal state is going to break time reversal. But we all live in contact with a heat bath, right?
Follow the arrow of time somehow. That's the
No, but wait. That's.
But if you do an experiment in completely isolated,
Let's wait.
The mechanics don't break the second law. This means that the entropy production doesn't go continuously up, but it doesn't go down with respect to the initial state. But this will work with arbitrary small systems.
If you give me 2 minutes, I show you some experimental results in a second. But to answer David's question, we all live in contact with the heat bath, right? And I try to explain irreversibility observed by putting a cup of coffee. The example I gave at the very beginning of the talk, why does heat flow from hot to cold? So I'm not talking about the beginning of the universe, I'm talking about everyday life, and we are in contact with the heat bath, right?
But Eric, do you have to assume isothermal processes and...
No, that's a simple situation.
I would say, sorry.
I'm just presenting their results.
Okay.
It's a simple situation where you see it immediately, and it's controversial enough. I can show you some very nice referral reports saying that you need 10 to the 24 particles. It's not true.
No.
It can be more general, but I'm going to hide behind the shoulders of Peter Hengi, and the claim is what it is, right?
Soldiers of giants.
That's well.
He's a giant.
Okay, so the conclusion here is that if the process is reversible, then clearly the mean work is equal to the free energy difference. It's irreversible if it's strictly larger, and it would be impossible, not observed, for something strictly smaller than the free energy difference. So the take-home message at this stage is irreversibility does not only occur in many body systems. And I'm doing this because I'm going to present results with one single spin. So experimental observation of the thermodynamic error of time. This is an experiment done in the group of Roberto Serra in São Paulo, Brazil. And what they have is a nice NMR setup. You have some chloroform molecules in the middle of the setup. You apply some magnetic fields to control everything, standard NMR setup. What is interesting is that there is one carbon atom here at the center, and they use the spin of this carbon atom as a two-level system. The spin, which they're going to investigate. I need to emphasize that the dynamics is unitary to a very, very good approximation, because the coherence time they have is of the order of several seconds. All the results I'm going to show you are taken below 1 millisecond, and they actually checked the unitarity of the dynamics. You can't forget the coupling to the heat bath. They need it to cool it down, and then they're so fast that they can forget the heat exchange with the environment. So it's unitary. Schrödinger dynamics, and that's for some people interested in that. You apply some magnetic field to actually drive the system away from equilibrium. So what you see here is the first experimental result. That's the non-equilibrium entropy production, which is defined in a standard way. That's the work that you do in the system minus the free energy difference. Would that be a reversible equilibrium transformation? The entropy production would vanish. Beta is 1 over the inverse temperature. So what they have is a two-level system. And then with the magnetic field, they'll change the level spacing, meaning in total you have 4 different transitions. Ground, ground, ground excited, 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 ground states, meaning you expect to have 4 different peaks because you have a quantized two-level system, and these are the 4 peaks that you see here. So this is the probability distribution of the entropy production, measured one. So what they actually measure is the work along the lines of what we heard yesterday. Two-time projective measurement approach with the twist that they do this Ramsey trick, but it's basically what they do. The mean value, the mean entropy production is here, red line, 0 is here. So clearly, the mean entropy production is positive here for a closed quantum system. And to my knowledge, this is the very first experimental verification that indeed what we teach all the students in the first or the second thermodynamics lecture, that delta S is, or entropy production is positive on average if you have a closed quantum system. Experimental proof.
How do they measure the
work?
delta F?
No, delta F is when they know. Give me a sec. You're going to. So they also. Now we need. So the mean entropy production. The entropy production has been determined. Now we need the connection with the arrow. And I'm going to use the idea of the movie. I'm going to play the movie forward and backward. In the experiment, the movie is played by the protocol. So you change the external magnetic field as a function of time with a forward process, and then you reverse it. So you start by preparing the system in initial thermal state. And now assume everything is at equilibrium. You drive slowly enough, so you stay at equilibrium. And you start in the equilibrium state, you end up when you always remain in the equilibrium state, meaning you end up in the equilibrium state, and then you reverse it, and you arrive at the same initial state. So this is a truly reversible system. Entropy production vanishes. If you do it quickly, you end up in a state which is a non-equilibrium state, meaning that if you do the reverse or the backward process by preparing the state in the final equilibrium state, apply the protocol backwards, there's going to be a difference between the forward and the backward result, and this distance is exactly the mean entropy production. That's what you expect intuitively. The faster the process, the further away from equilibrium, the larger the entropy production. And you can actually quantify this mathematically. You can derive that quite easily. The mean entropy production is nothing but the relative entropy between this state here, the forward, and the backward here. It follows from Schrödinger dynamics. You can find details in this paper that we published with Sebastian a few years back.
But is this because the reversal is not perfect, or there is an interaction with the outside, or whatever?
No, because you drive it away from equilibrium. The system is driven. The system is driven.
You drive it exactly the same way backwards?
Yeah, but you remember what I told you before. The initial condition breaks time reversal, right? So The initial condition is going to break time reversal symmetry. So this is
You
huge.
apply exactly the same unitary, the inverse of the unit that brought you forward. You should go back to the same initial state.
Like with a hidden assumption that you sort of dissipate at the end, right?
Yeah, no, that there is
And
a
that can-
perturbation. So this is like a spin engine.
Maybe you want to go, but
It's Loschmidt-Echo experiment.
but this is not exactly Low-Schmidt. But here,
Because there is a perturbation, so you don't apply exactly the same.
that's another argument. By assuming that you can reverse the protocol exactly, this the fact that you do not end up in a thermal state. That's the initial condition. It's not a Low-Schmidt-Echo experiment, but we can talk about that in more detail afterwards.
What are we seeing in this graph?
You can ask me what we're going to see in 10 slides. We're going to hopefully get there. So what you see here is what I'm going to explain now is the experimental result, right? So what you see here is, so in experiment, they were able to check or to determine both sides of that equation independently. So to determine the mean entropy production, they just need the distribution that I showed you in the slide before. And these are the the dashed lines here. And then they're able to do, that's the answer to your question, process tomography. Since it's a two-level system and they can control everything using NMR, they can reconstruct the density matrix of this two-level system at every single time during the process. So they know and you have very nice trajectories on the Bloch sphere in the paper if you're interested to know how they look like. And you see 3 different times. That's the duration of the protocol. The first one is a very long protocol, 700 microseconds. So you see that the entropy production is very small. That's what you expect because you slowly approach the quasi-static, quasi-reversible regime by getting slower and slower. If you do it faster and faster, the entropy production increases. And you also notice there's a very good agreement within error bars between this side and this side of the equation. For experimentalists asking why is there some small deviation, the reason why is because that's the main problem of NMR. The magnetic field is not completely homogeneous, and this small inhomogeneity leads to these small discrepancies. But hey, it's good enough, right? At least for a theoretician, within error bars, it's good, right? So this.
Yeah, I still don't understand. What is this time axis that I'm seeing there? Why is the entropy production not at all changing? What does this time tell us?
The time, the tau is the total duration of the process, and then each single time I do reconstruct my density matrix, and I can compare during, so it's exactly what you see here. These straight lines, I take this density matrix here, compare it with this here with this here, this here. This is what is shown here. Why it is constant?
Yes, exactly.
Because the dynamics is unitary. You can show in,
It's not a movie, it's just
but the move is reversing the magnetic field.
Collection of different experiments.
No, it's one experiment.
Each point is a different experiment.
No, it's an NMR. They just drive it and go back.
Each point is thousands of experiments.
Yeah, they do. They do average. Yeah, but
It's, in NMR you only measure average.
yeah, sure.
The average of the decision.
They have averages over 10 to 11 spin, something like that. Yes.
But
Yeah.
then you go back and you go to a different time and then you go back.
Meaning?
It's okay.
Okay. So this actually quantifies what you do expect, that the faster the protocol, the larger the entropy production, and this is one experimental demonstration of this error of time. Right? You have there's a distance. It characterizes the entropic distance between the forward and the backward process. It's like the movies of George Porter I showed you at the very beginning. Right? It's just the same. Just you play with the magnetic field. Now let me come.
There is a bath.
Sure, there's a cryostat. Right? There's a typical NMR setup. They have to cool everything down, and that's the initial state. And
But it's not obvious because the spin does not really interact with phonons.
no, but they cool it down, and then they have an effective temperature, which is the temperature of the spin.
What?
But this is a liquid.
Yeah,
It's a liquid state. So it's room
That's what
temperature.
I mean. So
it's room, but the effective temperature of the spin is a few nanokelvin. Okay.
The experiment is close to room temperature, right?
Yeah. But the effective temperature of the spin is a few nanokelvin. Is there an experimentalist expert in NMR in the room who can defend me? There is none. No.
but look, I think that it is an isolated system.
It is.
So
Dynamics is
so
unitary, but you prepare the initial thermal state somehow.
How? I mean, just artificially you've been not because it's not because it's in equilibrium with something.
Oh, for two-level system, any state is thermal in a sense.
Yeah, you may say that.
It's the weirdest talk I ever gave because the audience answers the question for myself. I should actually just play autofocus and just ask questions and answer.
You can sit down and relax.
Sure, that's what I should do. So I very much appreciate it, but it's a first. It's a first. But maybe
Take it as a compliment.
I take it as a compliment.
Control. He gives the talk, and
But you're the chairman. I'm just playing around, right?
You know, we cannot control ourselves.
But I'm happy that it triggers a heavy reaction. It's actually the intention of the talk, right? So let me reverse it, and I guess this is going to increase the number of questions exponentially. Let's do that. And let's start with conventional thermodynamics. What we teach students again is that we also always assume that systems are initially uncorrelated. So I'm going to come back to the cup of coffee. I'm going to put two systems together, and I want to check whether heat flows from hot to cold or from hot to cold, hot to cold or cold to hot. So in that conventional thermodynamics, that's what I talked about so far. There's a preferred direction of time. But now there's a number of theory papers, which you can find here, that consider systems that are initially correlated. Take two spins. The people doing quantum information for a living in the room, that's the typical system. You have two spins, two systems, they are quantum correlated. And then they argue that the direction of the arrow of time could be reversed, meaning concretely that heat could spontaneously flow from hot to cold. You put your hot of coffee, you come back after 20 minutes, it's boiling. The very first to put that forward to my knowledge was Partovi, 2008, and there's a series of papers by Jennings and Rudolph on that very topic. How can that be? So let me summarize with a nice picture what I mean. I have two systems, one is cold, one is hot. That's normal thermodynamics, no correlations between two. I put them together, thermal contact, and heat is going to flow from heat to cold until they thermalize. I'm going to focus on a slightly different situation. I still have my two systems, but now I correlated initially. And sometimes it can be that heat flows in the other direction, from cold to hot. Meaning the cold one gets colder, the hot one gets even hotter. And I'm going to focus on going to consider a concrete example, the one used in the experiment. Partovi used a different one, so it's not the only one. But I'm going to take two spins, two qubits, A and B, and I'm going to prepare them in the following state. So rho A and rho B are two thermal states. Gibbs states, each one is beta H, with two different temperatures. One is going to be hot, the other one is going to be cold, and then the initial state is going to have this additional term which kind of correlates them. There's a free parameter alpha. I'm going to consider two different values. The first value is alpha is equal to 0, so we clearly have two thermal states that are uncorrelated. And during the experiment, we're going to repeat the experiment by choosing another value, which is different from 0. And they are correlated. The important point to notice here is that this term is chosen in such a way that if you trace over A or over B, the reduced states are always locally thermal. If you look at one locally, it's a thermal state, well-defined temperature. You look at the other one locally, it's a thermal state, another well-defined temperature. So there's no non-equilibrium. They are locally thermal. And then we put them in contact, thermal contact, and this is implemented by using some random partial swaps. To get an intuition for that, this is like the random momentum exchange during the collision of two atoms. There's a nice PRL by Gisin and co-workers showing that indeed this leads to thermalization. And this is theory, and we did it Roberto did it in the experiment. So that's my only slide with some equations. Let's start by calculating. So I have my two spins. The two are isolated. I'm going to calculate the two heats. And that's very close to what Ram told us yesterday. It's a three-line derivation. You can show that the sum of the two entropy changes is always larger than the mutual information between the two systems. Probably find that in Perez's book on quantum theory, chapter 9, if I'm not mistaken. There's a chapter on information theory and thermodynamics. So I is the mutual information between the two systems. And now again, I'm going to consider two situations. The first situation is that they are initially uncorrelated, meaning the initial mutual information vanishes. And since the mutual information can only be positive, it's going, because of the interaction, because of the thermal contact, is going to increase, meaning that in that case, delta I is strictly positive. And since the system is isolated, QA is equal to minus QB, and you immediately derive that expression. And since TA is larger than TB, this cannot be positive, this is negative, QB has to be positive. That's Cannon Thermodynamics, chapter 1. Heat flows from hot to cold, meaning heat is defined such that it flows into the system. So the cold system, TB gets warmer. That's the standard error of time. Now, if you consider this situation where the two initial spins are initially correlated with a very large initial mutual information, it can be that as a result of the interaction that the mutual information actually decreases. So you have a negative delta I, and if you plug that in here, you can actually get that situation where you have a negative, smaller than 0. So this leads to the conclusion that QB is negative. Heat flows from cold to hot. And the error of time has been reversed. So that's the physics in a nutshell. The question is, when does this only shows that the reversal is possible. You want to know when does it occur? Is there a criterion for that? And the answer is yes, because you can calculate the heat flowing into system B exactly. It's a sum of 3 terms. The first one is the neutral information I showed you before, and then there are 2 relative entropies that characterize the entropy production. The same relative entropy that appeared in the first part of the talk. Right? So it's the entropy production, and the criterion is easy to see. This guy can be negative if delta I is much larger, much be larger than the negative of the one. So the entropy production is compensated by a negative mutual information. Lloyd says, it's the first one I know who really emphasized that this is possible. A very nice PRE in 1989. So there's a trade-off between information and entropy at the end of the day. And we heard on Monday the talk by Yuka that you can actually trade the initial, there's a trade-off between neutral information and entropy. It's another way of showing that, but applied to the error of time. So it's not too surprising. You can, there's a trade-off between information and entropy. And now you're all interested in seeing the experimental results. It's exactly the same setup, but now they're using 2 atoms of the chloroform molecule, the carbon atom here and the hydrogen atom there. They are prepared in 2 thermal states, 2 different temperatures, one hot, one cold. And the 2 are isolated from the environment over the duration of the experiment, and then you thermalize them by applying these partial swaps. So you do it by hand. And these are the experimental results. What you see here is the energy of spin A, the mean energy of spin B as a function of time, a few milliseconds. Let's focus on the blue dots. That's the uncorrelated case, and you see what you expect to see, namely the hot spin has a decreasing energy, and the cold spin has an increasing energy. So heat flows from hot to cold. At the same time, if you look here, where you see the neutral information as a function of time, it starts with a vanishing value, because they are not correlated. And because of the interaction, it slowly increases. For experts, I'm going to D in a second. Now let's correlate them by using the correlation I showed you before, and then suddenly you see that the hot spin is increasing is energy. So everything which is above the initial line corresponds to more energy. So heat flows in that case from the cold spin to the hot spin, which you see here again. The heat is the time derivative of the energy, meaning it's the difference between the energy at that time and the initial time. So this is clearly negative here, positive there. It's interesting to look at the mutual information as a function of time, and you see that there's a large initial mutual information, and this is decreased. It's traded. It's a trade-off between information and entropy. And what you see in the last plot here, D, that's the geometric quantum discord, which characterizes the quantumness of the initial correlation. And you see again that this quantum and the quantumness of the correlation decreases. So the correlation becomes more classical as a function of time. So we do have a system which is initially correlated, even non-classically correlated. The quantum correlation is the geometric quantum discord. The message here is that if you would apply naively in the second law of thermodynamics in its local form, you look at temperature of system A, temperature of system B, you would immediately predict, oh, heat is going to flow from hot to cold.
That's not the system. It's
not the system because you have non-local correlations. And if you apply the second law locally to a system which is non-local, you cannot get the right answer, right? So it's The last experimental result I would like to show you is we can actually calculate the spin for system B. As I showed you before, you have these three contributions, and these are the measured value of all of them. So you see that in the absence of correlations, the change of mutual information is positive and small, so there's no reversal. In that case, the change of mutual information is strongly negative, is 0 here. In that case, it does compensate the entropy production in the two spins. So that's the physics behind. If you really, again, I repeat it one more time because that's the main message. You can trade entropy or mutual information to decrease the entropy. And now you would say, hey, I have two spins. They're never going to really thermalize because we heard something about Poincaré recurrence. So it's going to flow back and forth. And you might say, can we do the same in a situation where we do reach a steady state? The answer is yes, numerically, not experimentally. Because that experiment is at the very limit of what they can do, even with NMR. So what you see here is a simulation of one spin coupled to n spins. N is going to be 2, 4, and 8. And you see here the mean energy of the system spin as a function of time. And you see two things. The first thing to notice is that in both cases, the more spins you have in the bath, the faster it reaches a steady state, as you expect, because they all collide, they all interact with each other. So that's a situation where you reach a steady state pretty quickly. And the other thing to notice is that there are two red lines. The first red line is the initial mean energy of the hot spin. And this line here is the average energy of the cold bath spins. And if you start with a situation where the spins are not correlated, so we correlate the system with one of the bath spins only, and you see that the energy fluctuates, but it's always in between the maximal value and the minimal value. Now you repeat the simulation in the case where they are correlated, the way I just described, and suddenly you realize that the hot spin gets hotter than the initial value. So heat was reversed, there's a heat flow into the hot spin. At the same time, it can also get colder than the coldest spins, meaning you had the reversal. That's the signature of the reversal. Clearly seen here for two spins in the environment. You go to 4, you still see them. Go to 8, you also see them. So there's a large reversal of the arrow of time, of the direction of the heat flow at the very beginning, and then because of the many collisions, you lose it. But the message here is that the reversals still occur, even though you couple it to an environment of 8 spins. Right? And the guess is if you increase the value of the initial mutual information, it could maybe extend it to a longer period of time. So let me conclude now. I don't want to know the time, but let me conclude. I told you many things, and I'm quite surprised. There was no question, hardly, on the second part. It's not what I had. Okay, sometimes you can be wrong. So there are 3 points I would like you to remember. Forget all the rest. The first point, which I think is important, is to realize that the arrow of time is not an abstract philosophical concept. It can be quantified and observed in the lab. The presented results of a quantum experiment, there are 2 more classical experiments, one done by Sergio Ciliberto, and the other one in collaboration with it's a colloidal particle, the other classical one, that's a collaboration with Chris using quantum dot. There are 2 classical experiments on the 2 experiments on the classical arrow of time. These are 2 on the quantum arrow of time. So when you quantify and observe. The second take-home message, it can be reversed in a system with initial quantum correlations. I repeat it many times, but I do it one more time. This is a trade-off between information and entropy. But not something which is a direct consequence of that is that most people would say the arrow of time is an absolute concept, right? It flows in the same direction for everyone, for every system. In that room, experiment in the lab, in some part, the experiment was done in Rio, you had a situation where the arrow you had a normal heat flow, normal arrow of time in the lab and everything around, but in the NMR machine, you had an arrow of time pointing in the other direction. So the arrow of time is not an absolute concept, it's a relative concept. Right? It depends on the initial condition, but that's what I'm repeating all the time, going back to Boltzmann. If you play with the initial condition, you can have an arrow flowing in the other direction. At the same time, it allows you to control the direction of the heat flow on the nanoscale, which is not completely uninteresting. And the last message is that, what I told you a few minutes ago, the local second law fails if you have no local correlations. And this is a very nice and I would say subtle interplay of quantum on the one hand and thermodynamics on the other hand. You use quantum correlations in the presence of a heat flow, it's quantum thermodynamics. Thanks.
See the
Plenty of questions.
So you can explain this reverse error of time without any relation to information or quantum. Take a very cold body, drop it on the floor, then it will hit this floor. So you have
And where does the energy come from?
from free energy. Simply correlated systems, they have higher free energy because entropy is smaller in comparison to energy. So a part of free energy, which is in this case, in this experiment, the gravitational potential, is transformed into heat. So everything is standard quantum thermodynamics.
But
This
this,
is
but this is
thermodynamics.
this is standard quantum thermodynamics, what I just presented. Right? No,
No,
yeah.
but this can be explained in a completely standard general thermodynamics terms using the notion of free energy and not only...
In the presence or absence of correlations?
Presence or absence of correlation means that the system has higher free energy than the two decoupled system at the same temperature. Classical correlation produces exactly the same
I never claimed that you do need quantum correlations to do that. Classical correlations do the job, sure.
But you do not need any concept of information. You need a standard concept of...
Well, but entropy is information.
Well, I look at, I mean, you are free to rewrite this using...
logarithmic number of possibilities.
That's the information.
No, but just for a second, this is math, right? This is the result of a derivation. There's the neutral information which appears. If you don't like it, you can make it disappear and express it in any other quantity. But this is math. There is no approximation. It's an exact calculation. The mutual information does appear. I'm not a magician.
There's nothing surprise in this because you have this standard, simple classical experiment that is exactly the same.
I should have done a poll at the beginning of the talk asking who believes that the error of time can be reversed. I'm pretty sure that 99.9% of the people that said, no way,
You should have
never.
asked who would like the error.
It's too late. I cannot go backward. I cannot go backward and change it.
So I guess we could spend months talking.
Endless. It's like talking about the quantum measurement problem, sure. But this is experiment. These are data, right? They're hardcore data. Heat flow, there's a heat flow in the opposite direction.
No, I have no problem with that. I guess
Good.
It's when you say that when you say that we can take the error of time and move it to the initial conditions and final conditions, one could just as easily say, I think it just moves the problem because you can just as easily say, why is there an initial condition and not a final condition? Nothing stops you from having a final condition.
And then,
So I don't think it necessarily gains us a lot by saying that, error of time comes from initial conditions. And I don't think you need to talk about cosmology to discuss this. We don't need to go back in time to the Big Bang. We can just say, why do we have initial conditions and not final conditions? And that's enough to kind of...
with that experiment, we chose them, so that's easy. For the direction of the planets in our solar system, I'm not sure if someone chose them for us. But I do agree, an experiment which we chose them, and they chose them, and then such a way that it works in one way or the other way.
Yes, but why are we always choosing initial conditions and not choosing final conditions? So, in some sense,
You want to say the miracle is still there.
the issue is still there. The issue is why initial conditions get set and not final
Sure.
conditions.
I don't claim to solve all the mysteries about the error of time. I just presented some theory, confirming experimental results, confirming that theory, so that we can start talking about hard facts and things that you can check in the lab. And if this motivates people to write more theory papers on the error of time about final initial conditions, I think my goal would be achieved.
Okay, quick. Who was number 3? I think that was you.
Thank you. So I have 2 comments. One is I think the error of time is not reversed. What happened is actually that what you see is that the classless inequality is not a good quantifier in general of the error of time. It's good when you don't have correlation. But for example, with this extended classless inequality, you see that you get that also with correlation. You just need to change the expectation value, and then you see that it's positive also in the presence of correlation. So it's an indication that you need to use a different entropy production measure, as I see it. That's a comment. Now about the experiments, which I'm very happy with the last one, okay? But the previous one you've shown, basically it was a completely unitary dynamic. There's no change in the entropy of the system, and there's no heat exchange, okay?
But there is entropy production.
No? Okay, so this is a delicate point.
But it's
You can calculate things, but there's no really entropy production. The movie, wait. The movie is, you agree, it's fully reversible. If I play it back, you will not be able to distinguish. What you calculate or what you show, you don't play back. You do different initial condition, right? You set it
I
to
reverse the
thermal.
protocol. It's the crux. It's the crux setup, yeah.
But
It's
you
the
also
crux
reverse
setup.
the initial condition.
Sure. I have to.
So, you don't have to.
But the reversal
You do
is
this in the
performed
course.
at the final stage, right?
Yes.
The reversal is performed on the state that you reach at the end of the forward protocol. You just go back to the start. You have to assume a further initial condition on the way back.
Because
The
it's
fact that you are not reversing it perfectly, because there is some very tiny interaction with the environment, which produces perturbation, and then you go to a different...
Yeah, but it's just the physics of the crux equality, and everyone in the room here knows what it is, and no one, the crux,
when you do it on a closed system, okay, it's not really entropy production.
It
It's
is.
a mathematical quantity.
no.
It's like
There's a very nice PRL by, please, the nice lady in Palma, Zambrini,
Yeah.
showing that you can do two things. You can have the isolated system, you drive it in a non-equilibrium state, not thermal state, calculate this entropy production. And then you can do the second experiment. The system is not truly isolated, right? So you let it relax after a while, and this entropy is going to be dissipated in the environment. And she shows the statistics is just the same. It verifies the same fluctuation theorem. That's what happens in the experiment. It's going to relax after a while. It's not truly
But it
unitary.
doesn't in this experiment.
But still, there's a difference between forward and backward. Crux, it's simply crux. Right?
We'll continue later.
Oh, but Chris, you wrote a review on that. Can you jump in and try to defend me?
Different language.
It's a different language, right?
Eric, I think there's a very easy way to put it. It's the difference between work minus change in non-equilibrium free energy and work minus change in equilibrium free energy.
Yeah.
And unfortunately, we don't have a terminology for distinguishing the two, and all these debates are about confused or mixing the two.
Shall we write a paper together on that?
Well, I did.
You did already. Yeah, well, so advertise it, right?
Nobody reads papers.
Here's a question.
What kind of correlations are you actually put? Like, maybe I missed this point, but what does it mean? Like, for the simplest setup, what do you have to do to have this kind of flow?
You need when you're asking what do I do to need
Yeah,
to.
I just so it's just best. So, okay.
I
You
didn't.
put best.
It's a sort of bed state which you put.
I was just wondering, like, that you have to spin. Maybe I missed just on the slide.
But it's.
You have this.
But the original paper by Partovi had a sum over Bell states, thermal sum over Bell states. You can do the same. But this was much easier to do an experiment than the sum of Bell states. But that's what he had, yeah.
So wouldn't you agree that there can be a sort of natural arrow of time, like the one you described, but then when you try to control the process, you may reverse it, yes? Of course, by doing the appropriate operations, and then you get sort of two completely different forms of evolution or arrows of time, what have you. How would you refer to this?
But there's a very nice, I'm going to hide behind someone again. Okay. There's a very nice PRL in a book written by Larry Schulman about having two different arrows of times in two coupled systems. A PRL maybe 10, 15 years ago, but he played with the electrodynamic arrow of time. And you have this, the forward and backward Green's function or whatever. I mean, it's Feynman-Wheeler and things like that. That's what they're using. But showing, he tried to argue that you can have two coupled systems with two different arrows of time. And this is a thermodynamic example of that, which in my opinion is much easier than the electrodynamic one.
But what he did was not thermodynamic.
No, but the origin PRL is electrodynamic arrow of time. Yeah. But then you can do, I think it has a follow-up paper talking about the thermodynamic arrow of time. It's...
Yeah, I'm not sure about...
No, I'm going not to defend everyone's papers during my talk, but it's just to tell you there is this paper now.
Okay.
So I'm sorry, I cannot.
I need coffee,
write the
right?
exact arrow of time, so we have to go now for the coffee.